All right, let's try to think about this. We have our atomic pool. It has an array of pointers to batches of memory. Same as before. We are keeping track of how many batches we've already allocated with its batch count variable. We are saving the object size that we are being passed during initialization. And we have this next available atomic variable that keeps track of the first item in our list of available objects. We then have a batch allocation mutex that protects the internal state of our allocator while we're executing a memory allocation for a new batch. Okay, this was good. Our initialization function sets the initial batch count to 0. It sets the pool's copy of object size to the one that we were passed. And it sets the value of the pool's next available variable to UN32max, giving us a signal that there's currently no object available for allocation. And we're doing this with memory order release as our synchronization operation just to be safe, even though we think that it's probably not needed because we are being protected by other synchronization operations. But for now, let's just use the safe option. We are initializing our mutex. And I think this looks good. So now let's go to our alloc function. We have a local copy of the allocator's next available variable, or the value of that variable. We are loading it. If the value is currently UN32max, that means we don't have any objects available for allocation. And we go into a mutex log. Since multiple threads can run into this case, we now need to double check that the pool's next available variable is still at the value that we expect, meaning it's still at UN32max. If it is, we check that we have batches left to be allocated, meaning batch count is less than batch count max. If it is, we alloc more memory with malloc, and we save a pointer to the allocated memory at index batch count in our pointer array. And we initialize all the objects in our newly allocated batch and set their next available index to the index of the object right before them in this array. This is the base pointer to our newly allocated batch, and we add to that I times pool object size in bytes. We cast that to a header. And we write an index of start index plus I minus 1, which is the index to the element before. We save that in the header's next available. And this kind of concludes the initialization of our batch. And we then set the pool's next available variable to the index of the last element of our newly allocated batch. We increment our batch count, and we update the local copy of the pool's next available and set it to index, meaning that our next available copy is now also pointing to the last element of this batch. We're calculating the batch index and index in batch to be able to get a pointer to the object at that location. Meaning we again take our base pointer and add to that the index in batch times the object size and cast that to a pointer. We want to look at this header's next available value. We read it here and make a local copy of that. And now we are trying to update the pool's next available variable and set it to our local copy, which is like the next element in the free list. And if the pool's next available variable is still equal to next available, which means that no other thread has accessed this variable in the meantime, we update it, we return true from the compare exchange function. And in that case, we return a pointer to the allocated object from our function. We don't go into another while loop iteration, and we have successfully allocated an object. If it returns false, we just continue here and enter another loop iteration, which means that our local next available variable is now set to the current value of the pool's next available value. And now we're going to do the same thing again. So for example, if we started off and, for example, read the index 1, or let's say index 0, which means in the initial state of our allocator, that means that there's one item left in the free list. We would have the batch index 0, index in batch would be equal to 1. We get this header, batch index would be 0 and index in batch would also be 0, which means we just get the base point of our backing memory. We would read the next available value, which would be equal to uint32 max. We would write that value to the pool variable, return true, and our allocator would be in the correct state. So this looks good. Now, one thing that we haven't handled so far, which is actually a very important point. Let me try to write a comment for that. Let's say the initial state of our allocator is that we have E0 and E1 in our free list, meaning that when we read the pool's next available variable, we're going to get a pointer to E1. We would now calculate the batch index, calculate the index in batch, and the header. This would be the header that we would return from the function. And we check again if our local copy is still up to date. And if it is, we return the pointer. But the way we check if our local value is still up to date is by just checking for equality with the pool's value. Meaning our local copy says E1 is available for allocation. And the pool says E1 is the last element of the free list. What could happen is that another thread reads the next available value from the pool, sees E1, removes it from the pool, therefore sets the head pointer to E0. And now another thread again puts, for example, E2 on the stack. And then thread 1 puts E1 back on the stack. If our first thread now checks for equality, that comparison would return true. So in the eyes of our thread, our local variable, our local copy of the head pointer to the free list is still equal to the head pointer of the allocator. They're both equal to E1. But our view of the world isn't equal to the view of the world of the allocator. Another element has been added to the free list that we don't know about. Meaning that if we read the next available index that is currently saved on E1, it would, or it might, still point to E0. Which would mean that, again, the comparison would return true. The comparison down here. And we would now try to set the pool's next available pointer to E0. Which means that by doing our allocation, we return E1 from the function. But we would set the next state of the allocator to now have E0 as the next available object for allocation. Meaning we've kind of forgotten about E2. E2 hasn't been allocated by anyone, but our view of the world, which wasn't up to date, has kind of caused this object to be lost. And this is a bit of a problem. Again, this can't happen in our mutex locked version of our allocator. But since we don't have any kind of other synchronization between multiple threads, we only have these atomic variables. This is something that can happen. And there's actually a pretty elegant and simple way to handle this. But since this video is already quite long, I think it's useful to have a bit of a break and go into details of how we're going to handle this problem in the next video. And after we've handled that, we're also going to implement our dalloc function using atomics. But for now, I think I'm quite happy with our current implementation. There's still some things for us to do. For example, we need to actually correctly think about all of our memory order arguments here and which ones actually require us to use release and which ones can be set to relaxed. But all of that will be handled in the next video. See you then. All right, change of plans. I think I actually have a bit of energy left. So let's try to go through this problem, or rather to the solution to this problem right now. The elegant and simple solution to the problem is to just have a generation as part of our atomic variable, meaning that with each write that we execute to the variable, we're going to increment a counter. So if you imagine our 32-bit value, we would have, let's say, 16 bits as a simple counter. And then the other 16 bits are the actual payload, which in our case it's just the index, composed of the batch index and the index inside each batch. And with each atomic write, we would increment this counter by 1. Let's try to come up with some kind of example for this. Let's say we have an atomic value v1, and we're just setting it to 0. On one thread, we might call atomic store. Actually, maybe it's not ideal to do this in some kind of artificial example, because we do actually need atomic compare exchange to really give an example of how this works. So we're setting the value of next available down here with our compare exchange function. Now, instead of just setting the value kind of blindly to a new value, let's incorporate this index into our atomic variable. Meaning that we're still just going to use 16 bits for our index, but we're going to add another 16 bits, or we're going to use these other 16 bits as an index that we're just going to increment with each call to atomic compare exchange or atomic store. So the way we're going to do that, we're not just going to have header next available. We're going to take the highest 16 bits and increment those by 1. And kind of the easiest way to do that is to just do header next available plus equals 1 shifted by 16. And that's basically it. So let's say we have the following value. We have, just going to write this in hex. We have these 16 bits as our counter, and these 16 bits as our payload. Let's say header next available is the value 1. If we add to that this value, we're going to get 1. So this is just the constant that we always add, which is this value right here. And we're going to add that to our header next available. And the result of that operation is 0001, this. We've kind of combined two values into one. These 16 bits are our payload, and these are our counter. So, for example, if header next available were already at, let's say, the value of 4, and we would add the constant value here to that, we would get 5 as our counter value and 1 as our payload. Pretty simple. And this also works if our counter is at the highest possible value. So let's say we are at the highest value only once in the upper 16 bits. Sorry, this is actually the value that I wanted. And we're going to increment this by 1. We are still going to get the correct result, which is just 0. We're kind of wrapping around our counter. And we still get our payload. And this is kind of the simple way to combine a counter and a payload into one value and use that to check if the pool's next available value has changed while we're doing other operations. If it hasn't, that means that our knowledge is still up to date and that the linked list is still in the same state that we expected it to. And if it has changed, that means we need to go into another loop iteration. Now, there is kind of an edge case with this. It is possible that, for example, we start off at a value of 0 as our counter value. We add 1 to that. We have our new payload and index. Meanwhile, another thread executes 2 to the 16 operations, causing our counter to wrap around and again be at index 0. Means we now read the value of the atomic variable again down here, and we will read a counter value of 0, meaning our compare exchange function is going to succeed despite 2 to the 16 operations having happened in that time. Now, I think this is fine for now. In the future, we could actually switch to use a uint 64 instead of a uint 32, but I think this is fine for now. We kind of understand the concept, and for now, this is the most important part. It's kind of unlikely that we have another thread that executes 2 to the 16 operations in the time that we do these couple of lines. So for now, we're just going to stick with our 32-bit value. So this is kind of a very simple way to make sure that the value of our atomic variable hasn't changed in the meantime. Now, we do this correctly in this call to compare exchange, but we do have another location that we need to check. Down here, we have an atomic store operation. In this case, it can't actually happen that another thread executes any lines of code while we are doing work here, because all of this is protected by a mutex. But I think we still need to make a change, because what we're doing right now is we're just writing the value index, which kind of implicitly means that we have set the highest 16 bits to 0, meaning we have 0 in these 16 bits and our payload, which is the index, in the lower 16 bits. And this could actually be a bit of a problem, because it might happen that another thread executes this alloc function and reads the counter value all once. If you increment this value, actually, this is not quite the case, because yeah, okay. Let's say we load our atomic variable and we read it with the counter value of all zeros and some kind of payload. That's the actual index. Another thread might now also read this atomic variable and it's also gonna set the counter implicitly to 0. Which means that if the first thread that read this value, if it now executes a compare exchange function, it's going to see all zeros as the counter value, despite another thread having allocated a whole new batch of elements. Meaning like previously, we made the argument that it's very unlikely that other threads executed 2 to the 16 allocations in the meantime while we're doing all of these operations in the alloc function. But if we just set it to 0, that might be an issue, because we might run into this case where the counters collide despite the state not being the same way easier. If our counter is already 0, that is a collision right away. And the simple way to fix that is to also just copy the counter value from the current value of next available. So we're just gonna OR our index value, the one that we set pool next available to, with the current value of the counter. And the way we do that is we do next available, and we only want the top 16 bits of this. Now, how do we do that? We have some 32-bit value, and we want a mask that is all ones in the top 16 bits and all zeros in the bottom 16 bits. The easiest way to do this that I can think of right now is to do one shifted by 16, which is going to result in 0, 0, 0, 1, and then zeros, minus 1, which is going to result in this, and then take the result of this and negate it. And this is how we get the mask that we want. So next available ended with 1 shifted by 16 minus 1. And I forgot parentheses. And to also signal to the user that this is actually all unsigned, let's put use right here. Let's also just write a quick comment of what we expect this mask to be. Yo, quick interruption. I was just watching the recording and I noticed a small but important mistake with this. We shouldn't just copy the current value of the counter from next available. We should actually do the same that we do in all the other locations, incremented by 1, and write this incremented value into our index variable. This is kind of the only thing I wanted to mention. You might have already seen it. Anyway, let's continue. Okay, and this is how we copy the current counter value into our index value that we set the pool's next available to. Okay. And I think that's kind of it. We are doing another store to the next available value. And this also needs to handle this case. So that's very easy to solve. Instead of passing a uint 32, we're just going to pass a uint 16, which means the value is just going to be meaning our counter is equal to 0. And the payload is uint16 max. Now that means that we need to change our alloc function. Now we are no longer checking against uint32 max, we are checking against uint16 max. And actually we are only checking the payload part of next available. So the way we do that is we AND this value with 1 shifted by 16 minus 1. Let's actually write a quick comment for this as well, of how the mask looks. And that's it. So 1 shifted by 16 minus 1, that's our index mask. And actually, let me add U's here as well. And the same value negated is our counter mask. And I think the way to make this a bit clearer is to define a couple of constants for those. So let's just take, actually forgot parentheses here. Let's take this value, delete it right here, and make two new constants here for index mask, which is this, and counter mask, which is going to be the inverse of index mask. Now, in theory, I think we can make this a bit clearer by casting this to uint 32. Because let's say index mask, like in the future, we increase our size of our atomic variable to 64 bits. We want to actually make sure that all the bits of our mask are set to 1, which means we need to be sure of the size of the index mask before negating its values to make sure that even the highest bit in this value is set to 1. And this should be fine. So instead of using uint 16 max, we can now just use our index mask. And right here, we can also use the index mask, just like this. Yes. We are ending our next available value with index mask, which means we only look at the lower 16 bits. And we are checking that all of those lower 16 bits are set by doing this equality check. And we also need to make this change down here. Again, we're ending it with our index mask and checking that it is equal to our index mask. Our start index is still uint 32, just like before. And this is also still fine because this is the next available value inside each of the objects. But down here, we now want to end this with our new counter mask, meaning we only look at the top 16 bits. And or the result of that with index, save the result in pool next available. Now we no longer need this comment. And this should now work. Next variable is going to be set to index. Okay, this is also in need of change, because next available now includes the counter and the index. But in this calculation down here, we only want the index. So what we do is we do next available and it with our index mask. And we're going to swap this out to use that index. We're still going to get the header pointer in the same way using batch index and index in batch. Those are now correct. We are loading again. Not again. We're loading the header's next available value. And we're just incrementing it by 1. So in this case, we don't need to use any kind of mask, since the addition just works this way. We're just shifting our 1 that we're trying to add into the correct position. So we're setting the value to header next available incremented by 1, checking if those are still equal. If they are, we have successfully allocated an object. If not, we enter into the next loop iteration. So this was it, I think. All right. I think we've now actually completed the most difficult part of this version of the allocator using atomics. The allocation part of this is going to be a lot more difficult than the deallocation part just because of this. We need to account for the fact that allocation can fail because we've depleted our current batch. We need to allocate a new batch using a mutex log and then kind of retry to do our allocation. Whereas in the deallocation case, we have much less work to do. Well, actually, we can just try to think about that now. What do we need to do? Our dealloc function is going to read the current value of next available. It is going to set the value of next available in the header of the object that we are trying to deallocate. And it's going to set the pool's next available to the index of the object that we're trying to deallocate. Basically, we're just appending it back at the start of the list. Kind of the same thing that we've done here using a mutex, but we now need to do it using atomics. So let's not change this. Let's create a second function. Pool atomic dealloc. Again, it takes a pointer to our pool. And again, it takes a pointer to the object that we're trying to deallocate. And now, as planned, we need to read the current value of the pool's next available variable. And that's going to be an atomic load operation. Again, we're doing it with an explicit synchronization operation, giving it a pointer to pool next available. And for now, we're going the safe route and using memory order acquire in this place. Now we also need to read actually, we don't need to read anything from I don't think we need to read anything from the object. I think the only thing that we need to do is, well, calculate our batch index and index in batch so that we're able to set the atomic variable to the correct value. And now we have a bit of a problem because we do have a pointer to the object, but we don't have its index in the batch and the batch index. And I think like there are kind of multiple ways to solve this, I guess. Since we do have the start pointers to all of our allocated batches, meaning we have this array of pointers and we have the size of each batch, which is object size times object count. So in theory, we could just loop through all of these pointers and test whether this pointer is within the region from the base pointer of the batch that we're looking at and the end of that specific batch. We can just use pointer arithmetic for that. Basically, if object pointer minus the base pointer of that specific batch is less than the size of a batch, we know that the object that we're trying to allocate here is part of that batch. And then we can do a pointer to object minus the base pointer to that batch divided by the size of each object to get our index in this batch. I don't think, honestly, that actually, I think it's a fine solution, but I'm not a big fan of looping through all of these pointers, to be honest. I'm not sure. I think for now it's actually easier if inside of our header we just save the index and batch index. Or actually, we don't even need to change. We don't even need to save the batch index and index and batch. We can just save the combined index that we have. So I'm just going to do uint32 index and initialize that value when we're allocating a new batch. So here we have our index, and we're just going to set header index to index. Pretty simple. And now inside of our dealloc function, we can now simply read this index. Header, we're just gonna cast Actually, we don't even need to create a local variable for this. Let's just do index of this object is equal to object casted to its header, which is the first element in the object. And simply get its index. So now we want to set pool next available to this index. But we also need to increment the counter again to make sure that no other thread is doing any operations in the meantime. So I don't think that we need this like header next available that we needed right here. I think we can just change our no, actually. Mm, no, we do need to create a second copy of this. But maybe let's call it next available new. The reason why we need a copy of this, we will again need to execute a compare exchange operation. And this compare exchange operation takes a pointer to the expected value. So we do need to hold on to that value that we've read. Okay, next available new is going to start off as just a copy of next available. And then we're going to, oh, actually, that's not even true. It's not going to start off as this. It's going to start off as index. And we need to increment the counter by 1 and or that with this value. So next available new odd with next available plus 1 shifted by 16. And we just want to have the counter, meaning we end the result with the counter mask. Okay, let's think about this. We've incremented the counter of our next available value by 1, which means we have a new counter value. We extract this counter value using the counter mask, and we OR the result of that operation with our index. And this produces the value that we are going to write. So now we need the same thing that we had before, where we have a local success variable and we do atomic compare exchange. Again, actually, we can just copy the logic from here. with our local success variable, we do the compare exchange. We are testing if our local copy of next available is still equal to the value that we expect. And if it is, we're going to save next available new as the new pointer to the start of our free list. And we do acquire, release, and acquire. That's correct. Or at least it's fine for now. And if it was successful, we don't return in this case. We're going to put this in a loop, including this. And on success, we're simply going to break from the loop, meaning that we have successfully put this object that we're trying to deallocate back on our free list. Let's have a close look at this. Take our object, cast it to its header, and read its index. We then load the current value of the free list pointer and we create the new value. So we have index, we OR it with the current value of the counter, incremented by 1. We extract the counter value. This is our new value that we're trying to save. So we set pool next available to next available new, but it's only successful if next available is still in the state that we expect it to be in, which means that if we don't have success, we are going into another loop iteration. Next available is going to be updated by the compare exchange. We increment this new counter value, extract it, OR it, and I think that should be it. Now, we haven't compiled and run this program for multiple hours at this point. So I definitely expect there to be syntax errors and other kinds of issues with this code. So that's kind of the next thing I want to do. I want to kind of duplicate our test function for the allocator that uses atomics, meaning we do a pool atomic test single threaded. Let's not copy the comment here. We're going to create our pool using pool atomic init, passing it our pool. We're still going to use a struct entity as our object size. We're still going to have a local copy of our entities array. All of this logic should still be the same. We now have to use pool atomic alloc. We're going to do the same kind of assertion. Like the API of our allocator shouldn't change at all. We've just changed a couple of internals. So it does make sense. We don't have to change a whole lot in these functions. We just need to insert the new name. And hopefully that's it. Again, I'm expecting there to be lots of issues, but let's see. Let's call pull atomic test single threaded. And let's see what kind of issues we get. Let's call our build script. All right. Let's try to go through this. Use of undeclared identifier true. Yes, we do need to include standard bool. No member named index in struct header. That is correct because we have invented the atomic version of this header and we aren't actually using it. Oh, okay. That also means that we need to invent. Okay, we actually have already an atomic version of our entity that has the atomic version of the header. Let's change our functions to use this atomic version of the header. So right here, when I change the type to header atomic, we need to do the same thing here. This should be fine. It's still called header internally. This cast also has to change. This is okay. Also atomic here. Oh, damn it. I changed the wrong function. Sorry for that. Let's do it correctly down here. Change it to atomic. Change it to atomic. Change this. Again, it's still called header, so we don't need to change the name. Just the types. I think that's actually already all the occurrences of this struct, at least in this function. Let's turn to our dealloc function. We have another one here. And that seems to be it. Are we using the header in this function as well? We aren't, but we need to change our entities to the atomic entities. Pool atomic, give it the pool, give it the atomic entities. We have our pointer array. Change this type. And hopefully that should be fine. Undeclared function atomic compare exchange explicit. Is it called differently? Oh yeah, we forgot the weak qualification. So instead of our, I think it was the on line 130, compare exchange weak explicit. Again, weak for now because we're executing it in a loop. We have a closer look at weak versus strong later. And we also forgot it down here. Undeclared identifier, memory order, acquire. Yes. Which line was this? 130 and 150. Yes, because in this case, it's actually written out. All right. And we do have an assertion failure. And the failure is that we expect the allocation to be null in this case, but it isn't. Meaning that we were able to allocate the first couple of batches, all of these objects. Those do actually return the correct, or at least a pointer that isn't null. But in this case, we don't return null. Now, I do remember that the first time we forgot to increment batch count, but this time we do actually do that. Meaning that there's something else wrong with this. So let's try to go through this. We read next available. And we are expecting it to be all ones in the lower 16 bits. So first of all, let's make sure that we've done this correctly. We are shifting 1 by 16 and subtracting 1. And for the counter mask, we are negating this value. Okay. We're locking the mutex. We are loading the value again. We're making sure that index mask is still all ones. We're making sure that batch count is less than batch count max. We're setting batch count to a newly allocated batch. We're setting the start index to batch count times object count. Batch count starts at 0. Which means for the first batch, we start at index 0. We go through our loop here. We get a pointer to the header of this object. That seems good. Let's actually make sure that the initialization looks okay. The initialization does look okay to me. We're taking a start index. Oh, I see a problem, but I'm not sure if it's the entire problem. As we've written here, the result of this operation is uint 32 max. But what we actually want is only the last or the first 16 bits to be set to 1. So we need to end the result of this operation with index mask. And right here, we said result is some counter value. And then in the lower in the lower 16 bits, it's going to be all ones. Let's actually put this on the next line. And we are setting our header to this, which means for the first object, it's going to be all ones, and in all other cases, it's going to be the index of the previous element. Now, it doesn't seem to me that that was the root cause, but let's try to execute this. And we are still returning null. So let's go on. We have our start index plus object count minus 1. That's the index of the last element in this newly allocated array. We have next available. We AND that with our counter mask and OR the result with our index. This looks fine. This is an issue. We are setting next available. Oh, actually, this isn't an issue. No. Because we actually do want next available to be to include the counter as well. Now, if we don't have any batches left, we set this allocation fail to true. But it seems to me that that isn't executed. Let's just put a print statement in here. And let's see if it's executed. It is never executed, which means batch count is never less. Oh, sorry, it's never equal to batch count max. So let's try to see all the increments of this variable. Allocation of batch. And let's see what we expect is for this to occur 4 times because we have an upper limit of 4 batches. And it seems to happen 3 times. B is less than batch. Yeah, okay. Well, sorry, no. No. So for some reason, I'm seeing multiple weird things. First of all, that the assertion failed line is above the allocation of batches, but I'm not sure if this is like the assertion failed. Might not use the same print buffer that we use. Just sort of interest. What happens if what happens if we just exit here? Okay, we're allocating 3 batches. What we expect to allocate 4. Interesting. Memory auto release. Okay, maybe it's actually an issue further down. Next available is equal to index. Unlock the mutex, which means that next available does actually have a valid value. We're dividing it to get the batch index, and we're getting the remainder to get the index inside the batch. This looks okay to me. Then we're getting the next available. We're incrementing it by 1. And on success, we return the header. Can't really see the issue with this. We have our batches here. We have the batch count, object size, next available. And our header atomic has the next available, and it has the index of the object. We're starting off with 0 batches, and we are setting next available to index mask. Now that should cause us on the first alloc to reach next available ANDed with index mask is equal to index mask. That's going to be the case on the first call to this function. We're going to log our mutex, and we'll set next available. We're just reading it again. The index mask should still be equal to all ones in the lower 16 bits. And batch count should just be 0. We're allocating memory. And the start index of this batch is 0 times object count. Then we're going through all the objects. We're taking a pointer to the header. All right. I have found another thing that looks wrong. We have called this index, which is actually a bad name. What it actually is the previous index. It's the index of the element right before the item that we are currently looking at. So our item is at start index plus I, but the previous item is at start index plus I minus 1. Which means that our index, which is header index, should actually be set to start index plus I. And now we can move it up one line as well. We're calculating pref index, previous index. And this is the value that we should set here. Okay. This is the index of the last object. That should be correct. We're saving that index into the allocator's next available variable and continuing our allocation. All right. This was definitely an issue, but I'm not sure if it solves everything. We are still allocating 3 batches. Which means that this is probably still going to fail. Yeah. So this was an issue, but it doesn't seem to be, it doesn't seem to solve everything. So let's continue to read this. All right, I've added another print statement here. Sorry, on this line that just prints the value of next available. Since we're just running it single threaded right now, it makes it a bit easier to debug. And I saw something interesting. The first time we go in here, we get a value of 65K, which is kind of the signal that we have run out of allocation space and need to allocate. So we go into this function, into this if branch, allocate memory, unlock the mutex, continue our loop. And now the next time the print statement is called, we get the value 1. And in the next iteration, the value is 0. Which means we have one failed allocation, we allocate a batch, then 2 successful operations. Then the next time alloc is called, we again get the signal again that we don't have any objects left to be allocated. We allocate another batch, followed by 4 successful allocations. And this is not correct. We've allocated one batch and are able to hand out. Oh, sorry, one thing I forgot to mention is that I've also changed the object count per batch to 2 to make it a bit easier to debug. So this is why we see 2 successful allocations, then 1 unsuccessful, followed by allocation of more backing memory. And then we see 4 successful allocations. And what this tells us is that we are not setting the end pointer correctly. Meaning, in our atomic alloc function, right here, we initialize our objects. And what we need to do is the last object of each newly allocated batch needs to have the index all ones in the lower 16 bits as its next available value. But the way we calculate it is we do start index plus I minus 1. So for the second batch, the start index is going to be 2. So this is going to be 2 plus 0 minus 1. And this is incorrect. The value should be UN16 max, but we're actually setting it to 1. And that causes us to think that object 1 is still available for allocation, but at this point we have already allocated object 1. Object 1 not being available is the whole reason why we had to allocate another batch. So this line is not correct. What we instead need to do, kind of the easiest thing we can do here, we create a variable for previous index. If I is equal to 0, we always set this value to index mask. Otherwise, we set it to this. And since we can now never have the case where start index is 0 and I is 0, meaning 0 plus 0 minus 1 would be uint 32 max. Since we can't have this case, we now can get rid of this masking with the index mask, like cutting out the first 16 bits. We're now basically guaranteed that the higher 16 bits are always 0. And set this index to the header's next available value. Let's run this now. And this is looking a lot better. So now we have one unsuccessful allocation, resulting in an allocation of a new batch, then two successful allocations, then another unsuccessful one, allocation of a new batch, again, two allocations that are successful, and so on. So instead of calling exit down here, now our assertion should hopefully be null. Yeah. This looks a lot better. We can actually get rid of our print statements now. Let's get rid of this line, as well as this line. This comment is... It is actually now correct. It wasn't correct previously. The comment had the right intention, but we didn't implement it correctly. Let's delete this print statement and run this again. And now we don't get an assertion failure. Very good. Okay. So I think the last thing I want to do is just to test very briefly if our multi-threaded test case also works correctly. So I'm basically just going to copy these two functions and create variants for our atomic allocator for them. So we have our pool. This is now an atomic entity. Same for this, we're now allocating from our atomic pool. We're going to assert that the result is not null. We need to give this a different name as well. Same for this. Again, we are creating an atomic pool. We have to call the atomic version of our init function. We give it the pool, we give it the same size of struct entity. We are creating our threads. We now want to start the atomic version of this function. We still wait for the execution to end. And let's try calling that. Let's just make sure that we still have thread sanitizer enabled. We do. Go back to our C file and try to execute this. And it doesn't give us any warnings. This looks pretty good. Again, I always say this, just because we don't get any assertion failures or warnings from the sanitizers doesn't mean that our code is 100% correct. It just gives us a little bit of a hint that what we've done isn't completely incorrect. All right. I think this was kind of enough for today. We kind of got a lot done. We we switched our allocator from using a mutex to using atomic values or atomic operations. We've created atomic variants of all our functions. We we learned about atomic operations in C. We have atomic load, atomic store, atomic compare exchange. And we've used those functions to build kind of a very simple atomics-based linked list. So yeah, I think I'm actually quite happy with this current state. And I think the only interesting thing that is left for us to do is to do a comparison between the mutex and the atomics-based version of our allocator. I'm not exactly sure yet what a good performance test would look like, but I kind of want to get a basic feel for the performance characteristics of using atomics versus mutexes. And even if this is not going to give us some definitive answer, maybe it's still going to be interesting. But as I said, I think it's enough for today, and we're going to do that performance test in the next video. Thanks a lot. See you then.